My name is Alex Martin, and I'm a graduate student studying phylogenetics and taxonomy of aquatic plants at the University of Kansas. Last summer, I worked for the Kansas Biological Survey, and my main focus was to study causes for cyanobacterial harmful algal blooms, also known as HABs, that occur annually in Marion Lake, which is located in central Kansas. Cyanobacterial harmful algal blooms severely degrade water quality for recreation and drinking water supplies. HABs are linked to increased nutrients like phosphorus in the water column, and we know Marion has been experiencing an increase in HABs since about the year 2000. We know that phosphorus, especially in dissolved forms, is a fuel that can reinforce HAB events. Phosphorus can be sourced either externally from watershed activities or internally from lake sediments. Phosphorus binds to iron, manganese, calcium, and other metals in oxygen-rich water and precipitates down into the sediments. However, when anoxic conditions occur at the bottom of a lake, phosphorus is unbound and released into the water as orthophosphate, possibly allowing it to fuel HAB events. Our goal for this study was to see if phosphorus release rates from Marion Lake sediments have changed in the last 13 years. We went out and collected sediment cores from 3 sites that were previously assigned by other researchers as seen in Figure 1. One site near the dam, one in the middle of the lake, and one site at the riverine. 4 cores were collected at each site and then transported to the Kansas Biological Survey. Core length was reduced to about 20 centimeters by releasing sediment out of the bottom of the core tubes, and then the water on the top was replaced with filtered lake water. All cores were aerated in a 20 degrees Celsius incubator for 24 hours, and then they were split into treatment groups. Oxic cores continued to be aerated, anoxic cores were bubbled with nitrogen gas, and hypoxic cores were reactively treated with air or nitrogen gas to maintain dissolved oxygen levels between 0.5 and 2 milligrams per liter. Water samples were collected on days 1 and 6 and sent to the Kansas State University for nutrient analysis, and then we calculated phosphorus release rates from that data. One of the most apparent physical changes we saw in the sediments was the formation of iron sulfide in the anoxic cores as seen in Figure 5, which indicated that we were able to maintain anaerobic conditions for the duration of the experiment. Anoxic and hypoxic treatments showed phosphorus being released, while oxic treatments showed both release and absorption into the sediments. Average phosphorus release rates for anoxic cores was 18.6 milligrams of phosphorus per meter squared per day. Previous studies on Marion Lake from Andy Jawalski showed release rates between 20.7 and 32.98 milligrams per phosphorus per meter squared per day. Although our cores showed slightly lower release rate values, they were still consistent with the range of data from other hypereutrophic lakes in the Midwest. Looking at the data we collected from this experiment, we came up with 3 hypotheses to explain why we continue to see an increase in harmful algal blooms in Marion. 1. Near-bottom anoxia is occurring more frequently, which increases annual internal phosphorus loading from lake sediments. 2. External loading of phosphorus from watershed activities has increased. And 3. Oxic internal loading is now occurring near the dam, which is also adding to annual internal phosphorus loading in the reservoir. This summer, we replicated this study 2 times, once from core samples during a drought period with no rain in the watershed for at least a week, and again within a few days following a rain event exceeding 0.5 inches per day. Cores were taken from 2 sites instead of 3, one at the dam and one near the opening to French Creek. We are currently waiting on nutrient analysis from this year's experiments to reaffirm the results we found in summer 2020, and to see the overall effect that rainfall and newly deposited sediments have on internal nutrient loading.